Hi everyone, and welcome to our module on drug elimination. Let's imagine that we took a drug and we injected it intravenously into a patient at time zero. I'm going to mark time zero on this graph of plasma concentration over time. I'm also going to mark it on this one over here. So we inject the drug intravenously at time zero, and the concentration therefore shoots up in the bloodstream. However, as time goes on, the concentration of the drug is going to fall because the body is eliminating it from the plasma. And it turns out there are two general patterns that drugs follow as they're eliminated from the body. The first pattern is a straight line like this over time, and we call that zero-order elimination. And the second pattern is a hyperbolic curve like this right here, and we call that first-order elimination. And we're going to talk about these two in the next few slides. So the first pattern of drug elimination is called zero-order elimination, and this is where there is a constant rate of elimination per time. Let me show you what I mean by that. So if we look at this chart down here in the middle of the screen, what we can see is that for each unit of time, for example, from here to here, we drop 5 units of plasma concentration, and then for another unit of time, we again drop 5 units of plasma concentration. So the rate of elimination per time in terms of plasma concentration is constant. And the reason this is called zero order is because the rate is equal to some constant, for example 5, times the drug concentration to the 0 power. And anything raised to the 0 power is 1, so we can just cross this out. So we call that zero order. There's no dependence or variation on the rate of elimination with the concentration of drug. And one thing that's important to know about zero-order elimination is there is no half-life for these drugs. So we'll talk about half-life in a minute, but half-life pertains to first-order elimination only. In zero-order elimination, it doesn't apply. The rate of decline is in units per time, not in percent of concentration per time, which is what half-life is. And there are 3 important drugs you need to know that generally follow zero-order elimination, especially when their concentrations get up to significant levels, and those are ethanol, phenytoin, and aspirin. And these are the 3 you should know for step 1. Now let's talk about first-order elimination, and this is the pattern of elimination that most drugs we use clinically follow. And in first-order elimination, the rate of elimination varies with the concentration of the drug. Let me explain what I mean by that. Let's look at this graph I've drawn on the screen here, and let's suppose we're operating in a system with a very high plasma concentration like what I'm marking on the y-axis here. Well, at that high plasma concentration, the change in plasma concentration over a unit of time might be very large, like 4. But once the plasma concentration gets lower, the change per unit of time will fall and become smaller, like 2 units. And then when we get even lower, it might fall all the way down to 1 units. So as opposed to the zero-order elimination where we were constant, remember I showed you 5 units, 5 units, 5 units, here we're changing from 4 units to 2 units to 1 units, varying with the concentration of the drug in the plasma. And the reason we call this first order is because the elimination rate is equal to some constant C times the drug concentration raised to a power of 1. And that's why it's called first order, which is different from zero order. And one thing that's important to know about first order elimination is even though the number of units per time that the concentration is changing is varying, it's falling from 4 to 2 to 1, the percent change is consistent over time. So the time it takes to fall from 4 to 2 is the same as the time it takes to fall from 2 to 1. And we call that the half-life, and half-life is an important measurement for all drugs that follow first order elimination. Let me just make the principle of half-life clear to you with a simple chart. So let's suppose that at time 0, we injected 10 grams of a medication into a patient, and that would represent 100% of the drug injected. At a time of 1 hour, let's suppose that the amount that's still present in the plasma fell from 10 down to 5. That would be a change of 5 grams. That would also be a change of 50% because we've gone from 100% down to 50%. Now let's look at 2 hours. At 2 hours, we might fall from 5 to 2.5 grams. That would be a change of 2.5 grams, but it would still be a change of 50% from where we were before. The same thing is true at 3 hours. So even though the change per hour is varying from 5 to 2.5 to 1.25, the percent change is constant at 50%. And this means we can define a number called the half-life, which represents the time it takes for the plasma concentration to fall by 50%. And this is a number that's only useful for drugs that follow first-order elimination. For drugs that follow zero-order elimination, we can just report the change in time, like 5 grams per time, because it's going to be constant, like that straight line I showed you before. Now let's talk about two special types of elimination which sometimes come up on board exams and you should be familiar with, and those are called flow-dependent and capacity-dependent elimination. There are some drugs that are metabolized so quickly that blood flow to the organ that metabolizes them, which is usually the liver, determines the elimination. In other words, if you send more blood flow to the organ, you get more elimination. If you send less, you get less. These drugs are called high extraction drugs, and there are a number of them that you can look up online if you wish. One example is morphine. So morphine gets virtually completely metabolized by the liver as it passes through, so its rate of elimination is dependent on the blood flow to the liver, and this means that patients who have heart failure can have a decreased clearance of morphine, for example, compared to someone who's got normal blood flow to the liver. That blood flow is determining the clearance of the drug from the body. Capacity-dependent elimination is elimination from the body that follows Michaelis-Menten kinetics, and I talk about Michaelis-Menten kinetics in detail in the module on enzymes, but for our purposes here, this means that the rate of elimination will be equal to Vmax times the concentration of the drug in the plasma divided by a constant Km plus the concentration of the drug in the plasma. And I talk about this in the module on enzymes, but when the concentration of the drug gets sufficiently high, this equation just operates at Vmax. In other words, the C over Km plus C cancels each other out, and the rate of elimination is just equal to Vmax. What this means for elimination of drugs is that drug elimination is saturatable. If you put the concentration of drug at a high enough level, the system will just operate at the Vmax rate. And when it's operating at a constant rate, that's zero order elimination. So the most important thing to know about capacity-dependent elimination is that drugs which obey this type of elimination generally follow zero-order kinetics, and that's because the concentration gets high enough, it saturates the enzymes, and then the rate of elimination will just be a straight line over time, like I showed you before, for zero-order kinetics. Now let's talk about a very simple but high-yield topic for step one, and that's how urine pH affects the elimination of drugs. You should know that many drugs are either weak acids or weak bases. So a weak acid is a drug that likes to give up a hydrogen atom. So it's some anion A and a hydrogen atom connected together, so we call it HA, and it can fall apart and become the anion plus a hydrogen molecule, like what I've shown right here. Weak bases are something like a base B connected to an OH molecule, and that can fall apart and become a positively charged base plus an OH negative molecule, like I've shown right here. Drugs, like many other things in the plasma, get filtered by the glomerulus and enter the nephron. Recall that the glomerulus filters most things in the plasma, and then it reabsorbs the things that the body wants to hold on to. The high yield point for you to know is that the ionized forms of drugs, that's the form that is positively or negatively charged, gets trapped in the urine after filtration, and it can't diffuse back into the circulation. So if we look at our weak acid equation right here, if the drug is in this form in the nephron, it will get reabsorbed, but if it's in this form, it will be trapped in the urine and go out of the body. For the base, if it's in this form, it will stay in the body and get reabsorbed, but however, if it's in the charged form here, it'll stay in the urine and get excreted. What this means is that the urine pH is going to affect drug excretion because the urine pH can favor either the ionized or unionized form of the drug. Let's talk about the weak acids first. So if you have a very acidic urine, that means you have a lot of H plus molecules present in the urine, and that's going to drive this equation this way because we're going to have so much H plus on this side, the equation is going to go this way and form the unionized form of the drug. This is going to get reabsorbed, so an acidic urine favors the reabsorption of weak acids. For the bases, it's the opposite. If we have a very high concentration of H plus in the urine, those H plus molecules are going to combine with the OH negative to form water. That is going to decrease the concentration of OH negative in the urine and drive the equation this way. So for weak bases, an acidic environment favors formation of the ionized form of the drug, and that gets excreted. What this means is that we can manipulate the excretion of drugs by altering the pH of the urine. So for weak acids, we want to alkalinize the urine to excrete more drug. In other words, we want to remove H plus from the urine so that we drive the equation this way for weak acids and form more of this A negative, which will get excreted. For weak bases, we want to acidify the urine to excrete more drug. In other words, for weak bases, we want to increase the amount of H plus in the urine. This will favor formation of the ionized form of the drug, and that will go on to get excreted. And the easy way to remember this is just that you want to do to the urine the opposite of the drug. So if the drug is an acid, then you want to alkalinize the urine to get it excreted. And if the drug is a base, then you want to acidify the urine to get more to be excreted. So this does have a clinical correlation in some rare circumstances. There are a couple of drugs that are weak acids. Phenobarbital and aspirin are two of them. And if patients overdose on these, you can administer sodium bicarbonate to alkalinize the urine and increase the rate of excretion. There are also a couple of drugs that are weak bases. Amphetamines and quinidine and phencyclidine are all weak bases, so you can administer ammonia chloride to acidify the urine in an overdose. Now this is really historical. Nobody does this anymore, and that's because the efficacy could not be established, and there is toxicity associated with causing a severe acidosis in a patient, so nobody really does this anymore. Final topic for this module is drug metabolism. So there are many liver reactions that metabolize drugs, and the pharmacology literature is replete with examples of all the different ways that drugs are chemically modified by the liver. But there's a couple that you should know as a medical student. First of all, you should know that the big picture is the liver wants to biotransform drugs into something that's easy to excrete. So they usually convert lipophilic drugs to hydrophilic products. And remember what I said, these hydrophilic products are water soluble and then they can be excreted in the urine. And there are two general classifications for all the different reactions that occur in the liver with drugs, and that is the phase 1 reactions and the phase 2 reactions. So the phase 1 metabolism reactions are generally reduction reactions, oxidation reactions, or hydrolysis. And you don't really need to know the organic chemistry of all this, you just need to know the names of the types of reaction. One thing you should know about phase 1 metabolism is that it often creates active metabolites. So the products of these reactions are usually not ready for excretion and they're usually still active. In fact, some drugs require a phase 1 reaction to activate them from a prodrug into their active form. Two other key facts to know are that phase 1 metabolism has been shown to slow down in elderly patients, so there does appear to be an age-related decline in the rate of these reactions. And then the second thing that's important to know about phase 1 metabolism is that this includes the very important cytochrome P450 system, which we'll talk about now. The cytochrome P450 system is a collection of intracellular enzymes that metabolize many drugs as part of phase 1. The clinical problem that comes up with the P450 system is that there are many drugs that inhibit or induce it. So you can imagine that patients are often on more than one drug. If one drug is being metabolized by P450 and another drug inhibits that system, it will alter the effects and the levels of that first drug. So if you inhibit the P450 system, drug levels can rise if a drug is being metabolized by P450. If you induce the system, drug levels can fall. So inhibitors of the P450 system are the most dangerous because these can cause drug levels to rise and this can lead to toxicity. Some important inhibitors worth knowing are cyclosporin, some macrolides, and the azole antifungals. Now luckily, many of the drugs that are metabolized by P450 are rarely used anymore. So for example, theophylline and cisapride, which is a GI drug, and terfenadine, these are all drugs that you'll hardly ever see used anymore. So the fact that the P450 system may be inhibited or induced by another drug is not that big a deal since very few patients are on these. There are a couple of clinically relevant possibilities. So I have seen patients on statins who were administered cyclosporin develop rhabdomyolysis. There are also many patients who take warfarin, and if they take an inhibitor of the P450 system concomitant with warfarin, their warfarin levels can rise and their INR can get very high. If you go online and look up a list of inducers and inhibitors of the P450 system, you'll find a huge list of drugs. And this is why we have pharmacists to help us out to make sure we don't have drug interactions. But some that you should certainly know for your boards in terms of inducers of the P450 system: chronic alcohol, rifampin, phenobarbital, carbamazepine, griseofluven, which is a fungal agent, and phenytoin. These can all induce the P450 system. And that means that a drug that's metabolized by P450 can see its levels start to fall and become subtherapeutic. The inhibitors, which remember I said are more dangerous, are drugs like isoniazid, antibiotics like erythromycin, cimetidine, azoles. Grapefruit juice has been described as inhibiting the P450 system, and ritonavir, which is an HIV medication. So if any of these drugs are given concomitantly with a drug that's metabolized by P450, that drug level can rise and potentially the patient can develop toxicity. Now let's talk about the phase 2 metabolism reactions, and these are generally conjugation reactions. They fall under the type of reactions called glucuronidation, acetylation, or sulfation. And once again, you don't need to know the organic chemistry of all these reactions, you should just be familiar with the names. And phase 2 metabolism generally produces very polar inactive metabolites that go to the kidney to get excreted. One place where the phase 2 metabolic reactions have some clinical relevance has to do with patients who are called slow acetylators. And these are patients who have a genetically mediated decrease in hepatic enzymes that acetylate drugs. Usually the enzyme is N-acetyltransferase. And studies have found that about 50% of Caucasians and African Americans are so-called slow acetylators. So acetylation is the main route of INH metabolism. So INH metabolism is slower in these patients who have a decrease in this enzymes. Now, interestingly, there have been no documented effect on adverse events, so it's not clear what the relevance of this is, but certainly it does affect the metabolism of the drug. Acetylation is also very important for sulfasalazine, an anti-inflammatory drug. And it's also very important for metabolism of procainamide and hydralazine. And you may know that these two drugs are two of the drugs that can cause drug-induced lupus. And since both drugs are metabolized by acetylation, people have looked at whether slow or fast acetylators get more drug-induced lupus. And it turns out that drug-induced lupus is more common among people who are slow acetylators. Now, it's not clear what to do with this clinically. We don't go testing people for their acetylation rate before we administer one of these drugs. But certainly the fact that some people have decreased levels of these acetylation enzymes has some relevance in the cause of drug-induced lupus. And that concludes our module on drug elimination.